All right, let's dive in. We're going to pull back the curtain on a concept that powers, well, pretty much every piece of software you touch every day. It's called object-oriented programming. Now, I know, it sounds super technical, but stick with me. It's really just a powerful way of thinking that lets us build the complex apps we can't live without. So, let's get into it.
So, let me ask you a question. What on earth could your favorite video game, with dragons and explosions, have in common with your boring old banking app? I mean, they couldn't be more different, right? Well, it turns out they're actually built on the exact same fundamental idea.
The secret? It's all about modeling the real world. That's it. Think about it. The game has digital characters and items, and your banking app has digital accounts and transactions. They're both just creating little digital versions of real-world things. And that, right there, is the heart of what we call object-oriented programming, or OOP for short.
Okay, so how do we actually build these digital models? Well, it all boils down to two really simple core ideas. It's all about the difference between a blueprint and the actual thing you build from it.
So, in the world of OOP, we call the blueprint a class, right? Look here. For a car, the class just lists out the potential properties. It's going to have a color, a brand, a max speed. It's the general idea of a car. But then we use that blueprint to create an object, and that's the actual car. See? It's not just any car. It's a specific red Tesla that can go 155 miles per hour. So you've got one blueprint, but you can build a whole garage full of unique objects from it.
Yep, to put it formally, a class is that blueprint. It's the template. I love the cookie cutter analogy. A class is the star-shaped cutter, but it's not the actual cookie. It just defines the shape and rules for what a cookie can be. It's the master plan.
And you guessed it, the object is the delicious cookie you actually get to eat. It's the real thing you create from the class. So using that one car blueprint, we can stamp out tons of different unique car objects. My car, your car, that really nice one your neighbor has, they're all based on the same plan, but each one is its own thing.
All right, so we've got our blueprints and our actual things, classes and objects. But now what? How do we make sure they all work together in a way that's not total chaos? That's where the 4 pillars of OOP come into play. You can think of these as the fundamental rules, almost like the laws of physics for this digital universe we're building.
Yep, there are 4 big ones, and each one is designed to solve a really specific problem, making our code way more organized, a lot more secure, and so much easier to reuse.
First up, pillar number 1, encapsulation. This one is all about keeping things neat, tidy, and safe.
So what is it? Encapsulation is basically the idea of bundling an object's data, its properties, and the actions it can perform all together into one single unit. The capsule in the name is a perfect analogy. A medicine capsule holds all its ingredients together and protects them from the outside. Encapsulation does the exact same thing for our code. It creates a protective barrier so you don't accidentally mess with an object's important data from somewhere else in the program.
Okay, pillar number 2. This one kind of builds on that idea of hiding things. It's called abstraction.
Abstraction is one of my favorites because it's all about making things simple. The whole idea is to hide all the complicated, messy stuff that's going on under the hood and just show the essential controls. The perfect example is your TV remote. You just see a volume up button. You press it, the volume goes up. Simple. You have no idea, and you don't need to know, about the circuit boards, the infrared signals, or the complex code making it happen. You just get the simple button that works. That's abstraction in a nutshell.
All right, moving on to our third pillar. This one is an absolute game changer for programmers. It's called inheritance, and its whole purpose is to save us from doing the same work over and over again.
So inheritance works just like it sounds. It lets us create a new class that, well, inherits all the properties and methods from an existing one. The family analogy is perfect here. Just like children inherit traits like eye color from their parents, a child class can inherit all the good stuff from a parent class. This means it gets a huge head start and doesn't have to be built from scratch.
Let's look at a concrete example. We could have a general parent class called vehicle, right? It has some basic properties like wheels and max speed. Now, instead of starting over, we can create a new child class called car that inherits from vehicle. Boom! The car automatically gets wheels and a max speed. And then we can add extra things that are specific only to cars, like number of doors. It's super efficient.
And that brings us to our 4th and final pillar. This one has the fanciest, most intimidating name of them all, polymorphism. It literally just means many forms.
But don't worry, the concept is actually pretty cool and not that scary. Polymorphism is the ability for different objects to respond to the same exact message in their own unique ways. Imagine you have a command called move. If you tell a bird object to move, it's going to fly. If you tell a fish object to move, it'll swim. And if you tell a car object to move, it'll drive. See, it's one single command, move, but it results in many different forms of action. And this is what makes our code incredibly flexible and powerful.
Okay, so we've got our blueprints, our objects, and these 4 fancy pillars: encapsulation, abstraction, inheritance, and polymorphism. But the big question is, why? Why do we care? What's the big payoff? Well, it turns out that putting all this together completely revolutionizes how we build software.
So here's the bottom line. With inheritance, we get massive code reusability. No more copy-pasting. Maintenance becomes a breeze. Because of encapsulation, if you find a bug, you just fix it in the one class blueprint, and poof, it's fixed for every single object created from it. It also makes your code way more intuitive, right? Because the structure of your code actually mirrors the logic of the real world. Plus, things like encapsulation and abstraction add layers of security, protecting data from being messed with. And finally, polymorphism gives us incredible flexibility to create dynamic systems that can adapt and change. It's a huge win all around.
And that really brings us to this key idea. Object-oriented programming is not just a way to write code, it's a way to think about and organize complexity. And that's the absolute truth. It's not about syntax or keywords, it's a mental framework. It's what allows a small team of developers to tackle these massive, mind-bogglingly complex systems, whether it's an entire online game world or a global banking network, by breaking them down into small, logical, manageable chunks. So there you have it. You now understand the basic principles for modeling pretty much anything you can imagine in code. So the question is, what would you build first? Would you model a system to organize your book collection? A simulation of your city? The possibilities are literally endless, and that is the true power of thinking in objects.